Making your own compiler or interpreter is the holy grail for programmers. Not only because it is an absolute joy to use something you created yourself, but also because you can shape it any way you want to, so it's tailored to fit you like a glove. I started Ford in the early 80s using a Sinclair ZX Spectrum. When the IBM PC became my main platform, the world had moved to Ford 83 and I simply hated it. So I switched to C instead. In the early 90s I had created a C function, which was in essence an RPN calculator. An RPN calculator is a very simple tool. Words are separated by white space, making parsing very easy, and it is governed by the 3 rules. If it's a command, execute it. If it's a number, throw it on the stack. If it's not a number, throw an exception. I wondered what it would take to make it into a full programming language, and one rainy night when I couldn't catch my sleep, I came up with a solution. And the result was called Ford. Number 4, lowercase t, uppercase h, not Ford. Although you pronounce it the same way, but it's not the same thing. And I will tell you why. Note, I will call it 4th throughout the video to make the distinction between 4th and Ford. Ford has a read, evaluate, print loop, just like Python. It's what makes a language interactive, so you can enter and execute statements at the prompt. In Ford you can calculate the result of 23 times 73 by entering 2373 star dot. And this is what happens the moment you hit enter. Ford has a structure called a dictionary. Every word in the dictionary can consist of a bit of code and or data. It is searched when the token has been parsed. In the case of 23, it doesn't match anything, so it is converted to a number and thrown on the stack. 73 gets exactly the same treatment. Star, however, is found in the dictionary, so its code is executed. It takes both values from the stack, multiplies them, and dumps the result back on the stack. Dot is found as well. It takes the number from the stack and displays it to the screen. The stack is empty now. That's how vanilla Ford works. At first sight, 4th seems to work the same. It creates a token, searches the dictionary, but it doesn't throw 23 on the stack. Instead, it compiles a bit of code that, when executed, throws the number 23 on the stack. Of course, the number 73 gets the very same treatment. The star is found in a dictionary and subsequently this code is added to the compilant. And the same is true for dot. Now, we've only been compiling, nothing has been executed. But if we execute the code generated, the result is exactly the same. The product of 23 and 73 is calculated, and the result is displayed as if we execute it straight away. Now let's have a look how an ordinary Ford compiler deals with the definition. The colon is a word like any other. It puts Ford into compilation mode and creates a new entry in a dictionary. When 23 is evaluated, it acts like the 4th compiler. It generates code that will put 23 on the stack when executed. The same for our other number, 73. The star will be found in the dictionary and its code will be added to the current definition. The same for our dot. Finally, the semicolon is found and executed. This one will add one piece of code to your definition, and that is exit, Ford's equivalent of what other programming languages call return. It also shuts down the compilation mode, so we can return to the interpreter. Okay, I'll let you in on a little secret. 4th does not have a dictionary. It has a symbol table. So, where does all the code go to? It ends up in what is called the code segment, an area of memory with its own address space. Every 48 instruction has an address, an operator and an optional operand. It's much like an assembly instruction. So when we compile 2373 star dot, the first instruction compiled pushes 23 on the stack. The second pushes 73 on the stack. The third contains the mul operator, but that doesn't strictly require an operand. So we put in a 0. We could have put in any other number without consequence, but 0 is fine. Dot doesn't require an operator either, so we use 0 as a filler. And there you have it. That's what 40H code looks like. But how does 40H deal with definitions? How does it prevent the interpreter from interpreting the body of the definition? Well, it simply jumps over it. It compiles a jump instruction even though it has no idea where to jump to. We will fill that in later. We know, however, where the body starts. It's right after the jump instruction. So we can create a symbol table entry. After that, the code is compiled as usual. When the semicolon is encountered, it compiles exit, just like ordinary Ford. But we can also see where our jump has to jump to, in this case address 010. So we resolve our jump instruction. Now, what happens when we call foo? Well, that's easy. It can be found in our symbol table, along with the instruction that has to be compiled. And that's exactly what will be compiled. Job done. But what about data definitions? First of all, words like colon are parsing words, which is pretty obvious since the name they define isn't in the dictionary yet. In 48, all parsing words are hard-coded, because nothing is interpreted. That also means that you can't extend the compiler with your own parsing words because when those words are executed, there's no source left to be parsed. Little fun fact, nothing is allocated while compiling. There's just a pointer keeping track of the allocations. So when we define a variable, we can create a symbol table entry containing the variable and its address. But absolutely nothing is compiled at this point. If we define an array of 5 elements, it's the same story. We can create a symbol table entry. The only thing different is that we have to reserve 5 elements instead of 1. So the pointer is increased 5 times. The next variable is no problem either. We got the pointer so we can make a symbol table entry and increment the pointer afterwards. So what happens when we refer to that variable or array during compilation? Well, that's that simple. It's got a symbol table entry, so the code associated with the symbol table entry can be compiled. Fetch is hard-coded, so that one's not a problem as well. Same goes for my. We have a symbol table entry for it, so it can be compiled, and fetch is simply a hard-coded word. Now the question is, not a bit of space has been allocated. So how does 40H know how much space to allocate when it is executed? That's easy. Look at the pointer. From its value, it's not too hard to calculate how much space must be allocated at runtime. And if you ask me, how does 40H do strings? Exactly the same, but a different pointer. Why? That we'll explain next time when we delve into the memory layout of 40H and some other miscellaneous subjects we failed to address today. Anyway, I'm Hans Bezemer and this was another episode of Back and Forth.